Hi everyone, welcome to a new week of online causal inference seminar. So today we are very pleased to have Professor Linbo Wang from University of Toronto to present the synthetic instrument from sparse association to sparse causation. So we also have the collaborator Dinka Wang to handle some of the questions. We also have Professor Zijian Guo from Zhejiang University as our discussant. So the questions today will be handled by Sarah. So Sarah, do you want to introduce this a little bit?
Yeah, I just wanted to remind you to please use the Q&A section instead of the chat to ask the questions, and then Dinke will be answering them while during the talk. And in the end of the talk, if there will be still some questions, maybe we can discuss them also with Linbo. So thank you for this, and then I wanted to invite Linbo to start the presentation.
Okay, great. Let me share my screen. Okay, I think it's this one. Okay, this is look good?
Yes.
Okay.
This is good.
Great. All right, great. So thank you very much for the introduction and the invitation. I'm very pleased to be here, I think, for the second time to share my ongoing work on causal inference with high or multivariate data. So this is based on joint work with Dinke Tang at the University of Ottawa, who will be at Q&A with us today, and my colleague Dehan Kong at the University of Toronto. So to get things started, I would like to first introduce our friend Zoe here, who is a biologist and an expert in mouse research. And Zoe is particularly interesting estimating the relationship between gene expressions and mouse body weight. Now, specifically, the scientific question she wants to answer is when it comes to regulating the mouse body weight, what are the key players among the thousands of genes that we can measure in a mouse? So to answer this data, she collects expression data on 3,000 genes from 300 mice. And based on her biological knowledge, she's confident to say that only a subset of these genes will be important for regulating the mouse body weight. Okay, so she has this data, and now she needs to run analysis to find out what these genes are. So she doesn't have a lot of background in statistics. So instead, what she did is she took a crash course in statistical learning. And from this crash course, she found this one method that's particularly suitable for this kind of problems, where you have large P, small a, and you have the sparsity assumption. And this is commonly known as a lasso model, right? So you first regress your outcome, which is body weight here, on these gene expressions, and based on the output from the lasso, then she can conclude that genes XYZ are important for regulation of mouse body weight. And these genes XYZ will correspond to the genes that have non-zero coefficients in the model. So of course, for this audience, there's no need to say that this is quite a problematic approach, right? In particular, there can be some confounders that will confound the relationship between gene expressions and the mouse body weight, right? So these confounders can be, for example, the diet this mouse is having, or whether or not they are active, or some batch effects. Right, we know that this can introduce spurious correlations between gene expressions and the mouse body weight. And a lot of these confounders, if we are being honest, will be latent. So the association that Zoe observed in the data between gene expressions and the body weight will come from two main sources. So one is what we call causation, right? Some of the genes will actually be causal genes for this body weight. So we might some part of this association might be due to this true causation, and another part of this may be due to this confounding. Right, some latent factors may introduce spurious correlations between gene expressions and body weight. So this, of course, brings up the well-known problem that causation is not association. But I want to emphasize that in this problem, there's a second layer of problem, which is remember our friend Zoe here is willing to make the sparsity assumption. But the sparsity assumption is on the causation, right? In that only a subset of these genes will causally affect the body weight. Whereas our lasso model is actually making the assumption of sparse association. So the difference between them is the confounding factor. But if we think about this problem, right, if these confounders come from some environmental factors, right, such as temperature or humidity in the lab, something like this, if they affect the expressions of genes, then this is likely going to affect the expressions of all the genes, or at least a majority of the genes. And if they also affect body weight, then this is going to induce spurious correlations between every one of these gene expressions or every one of these exposure and the outcome. So the association due to this confounding is typically quite dense. So what that means for us is the assumption of sparse causation is usually not the same as the assumption of sparse association. And in fact, if the confounding is dense, these two assumptions will not be compatible with each other. So what it means for this lasso output is it's well known that this is not going to give us the right causation. But in this case, it's not even going to give us the right association because it's assuming that the association is sparse, whereas in this case, we know that it's not. Right, so here's a quick recap of the problem here, which is, so our friend Zoe is willing to assume that causation is sparse, in that not all the genes will have will regulate body weight. And she's also happy to assume that everything is nice and linear. Okay, this can be a simplifying assumption, but in many cases, applied people are quite happy with just assuming linear models and go away. So now there are two main questions here. First is about identification. But is it even possible to estimate causal effects in this case? Well, you only have the measurements of the exposures and the outcome, and nothing else. And if it is possible, or if the causal effect is identifiable, then is there a simple estimator that will allow her to estimate these causal effects? So these will be the two questions that we're going to focus on today. So before doing that, let's take a step back and look at the setup here. So here we're considering a problem where we have multivariate exposure, a p-dimensional exposure, let's say x1 to xp, and a scalar y. So you can think of these exposures as the gene expressions and the outcome as the body weight. So this is known as the multi-cause setting in the literature and has been, I think, taken off in the last decade. Actually, can I move this? Okay, yes, I can move this. Okay, and our goal here will be going to try to estimate the causal effects of these exposures x1 through xp on y. And to do that, we're going to assume we have a structural equation model with independent error in that both the exposures x1 through xp and the y will be affected by some confounders u that we assume to be latent. So we don't observe this u. So here, this U, we assume this to be Q dimensional, and the Q is a number that's smaller than P. Okay. And to make things even simpler, we're going to assume that we have linear structure equation models, right? In that everything is linear. We can talk about how to relax the linearity assumptions later, but to focus on the main idea, let's first look at a case where everything is nice and linear. And so this will come back to this canonical problem of observational studies with unmeasured confounding. And then we know that due to this unmeasured confounding, in general, this causal effects beta will not be identifiable, but even if we have these linear models. So before talking about our approach, so let me first reveal what are the canonical approaches to deal with this problem. Right, so because this is a problem with unmeasured confounding, so I think the most celebrated approach is so-called instrumental variables. All right, so if we want to estimate causal effect of x1 on y here, then this approach will tell you go and find the instrument z1. If you can find such an instrument, then it's easy to estimate this beta 1. You can just run two steady squares. Right, in the first stage, you regress your x1, your exposure, the first exposure on your instrument. You get your x1 hat. In the second stage, you regress your y on x1 hat to get a consistent estimate of beta 1. Right, so this is this approach has been for more than a century now. Okay, but there's also a caveat to this approach is once you have an instrument, then it's great, right? As long as you believe in the linear models, then you can just run 2 linear regressions and you'll be fine. But in practice, it can be quite challenging to find the instrument. And remember in this case, because we have P treatments, so in general, we need to find P instruments. Right, so finding one instrument can already be quite challenging, and finding P instruments can be quite non-trivial. And an alternative approach for this latent confounding that's recently taken off in the causal inference community is called negative controls. Right, so there's some more general versions, but I'm looking at the simplest version where the basic assumption here says, we assume we know a priori there are some treatments that have 0 effects on the outcome. So suppose the outcome, the confounded U is of Q dimensional, then this negative control approach requires you to find Q treatments or Q exposures to have 0 effects on the outcome. So for Zoe, this will require her to have some prior knowledge based on her biological background, telling us these Q genes will have no effect on outcome on both body weight. But this assumption in practice can sometimes also be quite demanding. For example, our friend Zoe may say, but I don't know which genes have 0 effects. But this is what she wants to find out. All she can say is some of the genes have 0 effects, but she doesn't know which one. So this brings us back to the problem of causal inference under sparse causation. And these are our 2 main results. So the first result is about identification. It says that under some additional regularity conditions, which I'm going to talk about later, the causal effects are identifiable if and only if this causal effect itself, beta, is sparse enough. And how sparse we needed to the L0 norm, so number of non-zero elements in beta, to be less than or equal to P minus Q minus 1. So P is the number of exposures, Q is the dimension of the unmeasured confounded U. And if we do have such a sparse causal effect, then we also provide a simple estimation procedure that will allow you to find a consistent estimator of the causal effects. So these are just our 2 main results. I don't know if there are any questions. Okay, looks like it's okay. Okay, so right, so if we look at this result for a second, we realize that this is making a pretty bold claim, right? So saying that, remember, we only have access to the exposures and outcome, right? And the key assumption we're making here is just a sparsity assumption, which many people seem to believe that is quite weak. But we can use this to deal with the problem of unmeasured confounding. We can get away with unmeasured confounding by just using the sparsity assumption. So this seems, the claim seems to be pretty remarkable. So to first convince you that this is not entirely magic, let me first talk about this is actually identifiable. So I'm going to focus on a very simple model where I only have 3 exposures and 1 latent confounded U. And again, our Y is also a scalar. So we're going to assume linear models here, but these are not crucial. And our effect of interest or parameter of interest will be beta 1, 2, 3. So these are the causal effects of this X 1, 2, 3 on Y. And the key assumption we're going to make here is the sparse causation assumption, right? The L0 norm of beta is less than or equal to 1. So in other words, among these 3 potential causal effects, beta 1, 2, 3, at most one of them is non-zero, but we don't know which one. Okay, so this is the sparse causation assumption. So this is pretty difficult problem. So the strategy we're going to use is the so-called voting strategy, right? We're not going to solve this problem by ourselves. We're going to invite 3 experts to help us solve this problem altogether. So this is a very popular strategy. We did not invent this strategy. I think I first learned about this strategy from my former PhD advisor, Andrew Zhou, in the context of traditional Chinese medicine. And then also, I think in the causal inference literature, the first time I saw it was from Zi Jianguo's 2018 JSB paper, used voting strategy in the context of invalid IVs. And I think this is a very powerful strategy. And so let me explain. So now we have 3 experts for us. And each of these experts is going to assume that one of these beta is 0. Okay. And so first expert assume beta 1 0, second expert assume beta 2 is 0, third expert assume beta 3 is 0. Now, from this, for each of these experts, from the negative control literature, we know that for the first expert, since he assumes that beta 1 is 0, so she knows that the first treatment, X1, is a negative control treatment. And because our U here is also one-dimensional, so that information is enough for him to derive the causal effects for beta 2 and beta 3. So putting this together, he will be able to get a causal effect estimate for the whole vector beta 1, beta 3, beta 2, beta 3, which we call here beta tilde expert 1. Okay, similarly, the second expert, she assumed that beta 2 is equal to 0, so she can use this information also to get an estimate of the full causal effect vector. Similar with beta 3, with the third expert. Okay, now here comes our assumption. Our assumption says at most one of these beta is non-zero, right? So now let's just assume that beta 3 is non-zero, okay? So if this is the case, then what will happen is that the estimate from expert 1 will be very close to the true causal effect. The estimate from expert 2 will also be very close to a true causal effect because the assumptions they are making are correct. But for expert 3, because he's making a wrong assumption, so it's likely that his estimate will be can be far away from the truth. So of course, as outside as an analyst, we don't observe this underlying truth, right? So all we observe will be the estimates from the 3 experts. This is all we observe, have access to. Right? We don't know which expert is correct, which expert is wrong. But our sparsity assumption tells us that in this case, at most one of these expert, at most one of these beta is non-zero, which means if we translate to here, it tells us at most one of these experts can be incorrect. So in other words, at least 2 out of these 3 experts will be correct. And they will give you the same causal effect estimate. So obvious strategy to pick among these experts is to use a voting strategy, right? So in this case, because our sparsity assumption tells us that the majority among these experts are always correct, so we can let these experts vote against each other to figure out who is correct, who is wrong, right? So the sparsity assumption here, very interestingly, actually translates to the assumption that voting strategy will always work. And in a general case, I mean, this can be made much more general. So this, in a general case, we have P treatments, we have Q unmeasured confounders. Then what we show that is under some additional regularity conditions, and in the specifically, we're going to generalize this majority rule to a so-called plurality rule. But these are some details. But we're under that assumptions, we're able to show that this causal effect, causal effects of X on Y will be identifiable if at least Q plus 1 treatment effects are 0. Okay, so this number Q plus 1 is the sharp bound. This is the best you can get, right? It's both necessary and sufficient. So in other words, if you only have Q treatment effects that are zero, then you cannot identify the causal effect. And this makes sense because remember in the negative control setting, right? In a case where you know who are the which are the negative control treatments, in that case, you need Q treatment effects to be zero. So now we're in a case where we don't know which treatments have zero effects. So of course, Q is not enough, but Q plus 1 is already enough. So this is why this is necessary and sufficient. And I think what's more remarkable is that later we're going to show this number, this threshold is actually testable from data. So in other words, we can use data to tell us whether or not your causal effect is sparse enough. Right? So you don't have to guess something like this. Of course, you have to first tell me what Q is. But after that, I can use data to tell you whether or not your causal effect is sparse enough. Of course, under some additional modeling assumptions. And I also want to connect this result to the so-called multiply robust or doubly robust literature. I think this is quite an interesting. There's a quite interesting connection here. So I think for the audience here, a lot of us are familiar with the so-called doubly robust or multiple robust estimation procedures, right? So in that kind of procedures, you commit to a single causal model, right? For example, in double machine learning, you commit to the assumption of no unmeasured confounding. Then you specify multiple observed data models. And in the end, you say your estimator will be consistent or asymptotic normal as long as any one of these observed data model is right, and you don't need to know which one. But I think this our assumption, our results here, and in general, any results using the sparsity assumption can be formulated as some sort of multiple robust identification results, right? So, which means this result is robust under multiple causal models that involves unobserved data. So our identification result or our identification formula will hold if the first Q treatment effect is zero, or the next Q treatment effect zero, or any Q out of this P treatment effect at zero. Right? These are different causal models, but they all give us the same identification result. So I think this is there's an interesting connection or comparison with multiple robust estimation literature. Okay, let's aside. Anyway, so I think voting is great, especially for sparsity, for sparse models. But we're only halfway through, so there must be some problems with voting. And I think a general problem with voting is it can be when there are many experts, then the voting strategy can become quite challenging, both computationally and statistically. So if we think about the general case, right, we have P treatments and the Q unmeasured confounding. So in this case, each expert will need to assume that Q treatment effects are zero. So how many possible experts we can have, right? We have P treatments. Each one assume Q is zero, Q of them is zero. So in general, we can have P choose the number of Q experts. So if we want to actually do this voting procedure, then we need to, for each of these experts, we need to evaluate the causal effect based on their assumption. Then I think what's more challenging is that at the end of the day, we need to compare their causal effect estimates across these pictures, the number of Q experts. And because we are now in a finite sample case, we also need to deal with this estimation error or estimation uncertainty. So which this will mean we need to compare P choose the number of Q P dimensional estimates and figure out whether or not they agree with each other. So this can become quite challenging if at all feasible. And there is also, of course, the statistical challenge of inference after model selection, because we first figure out which experts are correct, then base our inference on these correct experts. So this is a canonical problem of inference after model selection. So our solution, this is in the title of the talk, is called a synthetic instrument. So we need to make some additional assumption, and this assumption is a factor model on the treatment model on the treatment X. So X equals lambda U plus epsilon X. So this is nothing but a standard factor model. So here we observe a p-dimensional vector X, and we assume that this have a factor model according to U. And we also assume that we have access to a good estimator of lambda. Right, so here we don't make any particular assumptions on epsilon X, as long as we are still able to obtain to be able to estimate lambda. So I think the standard approach dates back to Anderson and Rubin is to assume that this we have a diagonal structure. So all these epsilon X are independent, uncorrelated with each other. Then of course, we can estimate lambda when Q is smaller than, I think, I like Q smaller, small relative to P. But there are also some more recent advances that allow us to estimate lambda, even when we have a dependence among this error structure, and X can be high dimensional. So I'm not going into details of that literature, but I'm just going to assume that whatever they do there makes sense. They are going to give me a good enough estimate of lambda. And as a return, what we can provide is what we call multiple robust causal inference that are valid regardless of which set of the experts are correct. Right, compare with the naive approach, where you first identify the set of correct experts and then do post-selection inference using a selected set. Our approach tries to bypass the model selection step altogether. Right? So in other, or if you want to think about another way, we do this selection and estimation in the same step. So here's the main idea. So again, let's focus on the simple setting where we have 3 exposures and the scalar measure confounded U. So in this case, our factor model for X will just be X1 equals alpha 1 U plus epsilon 1, X2 equals alpha 2 U plus epsilon 2, and X3 equals alpha 3 U plus epsilon 3. Right, everything here in these models are scalar, right? There's no vector here. And using standard factor analysis, we can already identify these coefficients alpha 1, alpha 2, alpha 3. Now, the idea of this synthetic instrument is that we first realize what's causing the problem here. It's the yield, it's the unmeasured confounded yield, right? So we're trying to get rid of yield. And how we get rid of yield is we can, if we just, let's say, if you just look at the first 2 equations here, you'll quickly realize that in order to get rid of yield, you just need to take linear combinations of x1 and x2. And in particular, if you take s1 minus alpha 1 divided by alpha 2 times x2, then this u term will cancel out. And you are left with this epsilon term here. Okay, this is what we call synthetic instrument. And similarly, if you do 2 and 3, you can similarly get another synthetic instrument. So this synthetic instrument, although they are just functions of x, they no longer depend on yield, so they are purely noise. So, and we know that noise are the best instruments we can get for this treatment. And we can rigorously show that these synthetic instruments, these are indeed valid instruments for X, for the treatment. But unlike standard instruments, right here, this is an important difference between a synthetic instrument and the usual instrument that the people use is that our synthetic instruments are synthetic. You don't need to go anywhere else. You don't need to go to your domain experts. You don't need to, in the case of Mendelian randomization, you collect additional data, right, to find the instruments. Here, you just you get some instruments from the treatments themselves. Okay, so these are called synthetic instruments. And after you have these synthetic instruments, and these are just, then you can use this just as any other instrument. Okay, you can run your 2 CT squares So in particular, in the first stage, you regress your treatments on this synthetic instrument. In the second stage, and you get a X hat. In the second stage, you regress a Y on X hat. Of course, if you look at this, there's still one caveat here because the treatment is, in this case, 3-dimensional. And the synthetic instrument in this case is only 2-dimensional. So in general, you cannot, the second stage, you will have some collinearity problem here because you cannot identify 3 treatment effects with just 2 instruments. But don't forget, we also have this sparsity constraint. Right? Our sparsity constraint says, in this case, at most one of these beta is non-zero. And with this additional sparsity constraint, then the whole thing works, right? The second stage, there's a unique solution. So here are the main result for identifiability under these model assumptions. So under our modeling assumptions, the following 3 statements are equivalent. The first one says the treatment effect beta is sparse enough. The second statement says the causal effect beta is identifiable from this 2-stage square I just described to you. And the third condition says the most sparse least square solution to the second stage regression has L0 norm smaller than P minus Q. So in other words, you run the second stage regression, you find the most sparse least square solution. And you compare the L0 norm of your solution with P minus Q. So the last condition here is testable, right? It entirely depends on the observed data. And because all of these are equivalent, this tells you that you can, from observed data, run these regressions and tell if your causal effect is sparse enough and if your causal effect are identifiable. So this will be the full synthetic 2-stage square estimator. So in the first stage, you regress your treatment on a synthetic instrument, you get X hat. In the second stage, you regress the Y on X hat subject to some sparsity constraint. Then you can select the tuning parameter using your favorite technique. And you're going to estimate the sparsity level for your beta. In the third step, you compare the sparsity level of beta, which I call S hat here, versus P minus Q hat. If S hat is smaller than P minus Q hat, then you report the estimate of beta. Otherwise, you report that beta is not identifiable. Okay, and we also have some theoretical results. These are very similar to the same very similar result to that you get for the lasso model. So I'm going to skip here and just go to the see how these things play out in the obesity data set in the motivating example I mentioned to you. So we have data from 334 mice fed on a Western diet for 16 weeks. Now we also have gene expression data of the liver tissues for about 23,000 genes. And we also have measurements of their body weight. So this is all we need, right? This is the first 3 lines, or actually these 2 lines are all the data we use for our analysis. But this data set also happen to have some genotype data. About 1,000 SNPs. So you can actually also run Mendelian randomization, and Lin et al. In a 2015 JASA paper actually apply Mendelian randomization to this data set. So they select 17 genes that are likely to affect mouse body weight. So what we are going to do is that we are going to replicate this analysis, but we are going to ignore this genotype data because you don't always have access to this genotype data. We are only going to use this gene expression data and the body weight and to see what we can get. So we're going to follow the same quality control procedure. So we're left with about 300 mice and expression data of 2,800 genes, and adjust for sex. So the way we did this is we first use factor analysis to estimate the number of factors. And this will give us a Q hat equals 3. Then we run this synthetic instrument. And this synthetic instrument will identify 5 genes for us. So before looking at what these 5 genes are, we first check the identification assumptions. So remember, the identification assumption says the sparsity level 5 here needs to be smaller than p minus q. So our p here is almost 3000, and our q here is 3, right? So what we get is 5 is less than 3000 minus 3. So you can see that usually, and this is very common in a lot of other data sets we try, right? These identification assumptions are very weak, and it's very easy to satisfy. You can even if I I get a conservative estimate of Q hat to be 300, it's still going to be within this identifiability range. So usually the identifiability is not a problem. Okay, and coming back to this, this synthetic two-stage square identify 5 genes. The first gene is, I think, believe this is called insulin growth factor binding protein 2 gene. So this is a gene that's known to prevent the development of obesity and protect against insulin resistance. And this one is the one with the largest effect size. And it is also the only overlap between our results and the MR results. So we also find 4 other genes. Among these 4, there are 3 that we found some evidence from the literature that this is actually this is going to have some effects on the body weight. We cannot confirm the effect size, but at least the direction of these effects will be consistent with what we already know. There's only one gene that seems to be new to the literature. Okay, so I think I'm going to have a quick summary here. So I think people now realize that sparsity is a common feature of modern data sets. Or even if the sparsity is not true, I like what is in elements of statistical learning, there's what they call a bet on sparsity principle. Right? So you use a procedure that performs well in sparse settings, since no procedure performs well in dense settings. But I think there's a key difference between the approach we're taking here and the classical high-dimensional statistics literature. In the classical high-dimensional statistics literature, often assume that the associations are sparse. But I think in a lot of cases, because the sparsity comes from assumptions made by humans, and in a lot of cases, human can most reason about causation. So sparse causation will often be more plausible. And so we look at the problem of causal inference under a sparse causation. And I think sparsity combined with the voting strategy is a very powerful tool for causal identification. It will replace a lot of some conventional strong conditional independence assumptions into this simpler structure. And usually once you adopt this strategy, I think you usually almost always get some multiple robustness for free, as I said. Because sparsity, the assumption of sparsity itself is a multiple robust assumption, because it doesn't specify which of these coefficients are 0, right? But in the end, it will give you the same identification result. But I think one challenge to using this voting across any kind of causal identification problem is the estimation problem. So in particular, if you want to use voting, you need to compare estimates among different experts. And this can be challenging if you are in a finite sample setting and if you have a lot of experts to deal with. And I think the multi-cause problem that we consider here has a very nice structure that allows us to develop the so-called synthetic instrument as a powerful tool for estimation. So this bypasses the selection among the multiple experts. So it gives you a procedure that's very easy to implement, and computationally it's quite efficient, and we also have an R package if you are interested in trying it out. So finally, I would like to discuss, as promised, some extensions to nonlinear models, right? Because I want to see what's the limit of this approach. All right, so for now, we are assuming both the treatment and outcome models are linear. right? So what are we doing at the end of the day, right? If we take a step back, think about if you come from instrumental variable model perspective, all we are doing is we use the first factor model to create P minus Q instruments. That's all we are doing, right? So there are multiple ways to get instrumental variables. You can go to your nest or experts, or you can collect a lot of genetics data set, or you can just assume a factor model. And assuming a factor model, P treatments can give you P minus Q instrument. And you can use these P minus Q instruments to identify the treatment effects. Of course, you cannot use this to identify the original P treatments because P minus Q it will always be less than P. But as long as the sparsity level of the treatment effect S is less than P minus Q, then you're good. You can always use the P minus Q instruments to identify S treatment effects as long as S is smaller than P minus Q. There's no need to collect additional data to go to anyone else. You just assume a factor model. And it seems that people are very happy with factor models. We have been assuming that for more than a century now. Of course, the way if you want to take this one step further is now you can consider some non-parametric factor analysis, right? If you want to, because at the end of the day, you are trying to get rid of U. That's the key idea, right? As long as you can get rid of U, then you can get the instruments. So if you want to do this, although I think this can be can be non-trivial, at least I don't know how to do it right now, is in the more general case, how do you find f such that f of x doesn't depend on U? Okay, so if you instead come from a factor model perspective, where can this take you? Right, so the this structural model approach actually, so the key assumption here we're making here is the epsilon x is independent of U compared with the standard factor model, right? In the standard factor model, you usually only assume the epsilon x is uncorrelated with U. But here, if you treat this model as a causal model, then usually in a non-parametric structure equation model, you assume that the errors are independent. So you go from the uncorrelatedness to independence. And this seemingly small step will give you a lot of identification power. Because this then we can account for arbitrary dependence between U and Y. It's based on a very simple fact that as long as you assume that epsilon x independent of U, then any function of epsilon x will be independent of any function of U. All right, so this is for causal people, this is not surprising, right? Because we know that one of the main advantage of instrumental variable is that it can deal with arbitrary dependence on U. And you don't need to know the specific form of U. So for causal people, if you look at this problem from a causal inference perspective, this is not surprising at all. But for people from a factor model perspective, and just as a background, a lot of people, a lot of experts from the high dimensional estimation or the factor model literature, they also investigate this problem. But they also always have trouble dealing with a case where this G is nonlinear. Okay, almost all, if you look at this paper, almost always they assume that Y will depend linearly on U. And this seems to be a major problem of how to extend this from a factor model perspective. But from a causal inference perspective, this is almost trivial, or at least as long as you are willing to assume that epsilon x independent of U, then you will get any function of epsilon x independent of any function of U. So we can account for any nonlinear causal effects, right? Because now we have instruments. And we know that instruments can help us to identify causal effects, not only for linear causal effects, but also for nonlinear causal effects. Okay, So we can look at GRM where this with a non-link function. We can also make this more general with single index model, or we can make this as additive models. But because at the end of the day, we have instruments, we can do what other instruments can do. This is bottom. Okay, the paper is on archive. Package is also online. You can get a link here, or if you go to my website, there's a link for the R package. Yeah, and yeah, I will stop here and happy to take questions.
Thank you so much, Linbo, for the very nice talk. Actually, we received a lot of questions, but I just wanted to shout out to Dinko on doing a fantastic job in quickly addressing many of them. So this gives us opportunities to like stay on time, and we can probably transition to our discussion at this point. And our speaker and Q&A moderator can continue with answering some of the questions from the audience.
Okay,
Thank you so
maybe I
much.
should stop sharing.
Yeah, Zijian, feel free to share your screen.
I can still see Linbo's screen.
Wait. Okay, yeah, sorry.
Okay, I think now I can give it a
Good.
try.
Okay.
Okay. So you can see my slides, right? So
Yeah.
we also try to moving. So now it's a full screen, is it?
Yes. Perfect.
Okay. Yeah. Thank you everyone for having me here, and also I first would like to congratulate Linbo and his co-authors for a very nice paper. So another very nice paper from Linbo, and I read several of them before, and I'm very honored I can discuss his work today. So in my discussion, I will first sorry, it's not moving. Okay. I'll divide it into two parts. In the first part, I'll summarize a bit what Linbo is doing. It's basically like what I got from reading his paper and also the slides he sent to me. And this is basically repeating what Linbo is doing, has done. And then I will do a bit discussion and also connection to some existing literature. And also I will ask some questions, like just from my own view, may not be the best question. Okay. So this is the model that Linbo is considering, like this hidden confounding model, and X is the treatment, the multidimensional exposure, and U is a unmeasured confounder, and they link together by this factor model. And I'm just looking at the simplest one, assuming all the effects they're linear. And I very much like their paper, like they have a very good example. They say, let's just consider there are 3 exposures and then there's 1 hidden factor. So just U is 1 dimension and the X is 3 dimensions. So this is just enough to illustrate the main point and doesn't make the problem too complicated. Okay, so that's my main way of looking at the problem. So I think the first part I find very interesting is they do a covariance between xj and y. And then if you just plug in the outcome model y, there are 3 covariates and some unmeasured confounder, then they can have this system of equations. Okay, and if you look at this carefully, then beta 1, beta 2, and beta 3, and that they are very naturally coming out. And this lambda j is coming out just because of this unmeasured confounder. Okay, and we can imagine we do this like a system equation, so like 3 times, and then we just have 3 equations because we have 3 covariates, and then like, but we now have 4 like unknowns, like beta 1 to beta 3, and also the gamma. So that's why it motivates Linbo to make this like a sparsity assumption, or it's very natural, as he explained, to make this sparsity assumption, and also like to help us to do the identification. Okay, so by the way, I would like to clarify that to be very precise, I do a few screenshots from Linbo's paper. So this is the exact screenshot. Okay, and then here is their voting mechanism motivated by the previous slide. They say there are more equations, there are less equations than the parameter they want to estimate. Then one way is to leverage the sparsity assumption. So as Linbo explained, so they can first assume the beta 1 equal to 0, and then they solve the system equation, because now they only have 3 parameters, 3 free parameters and 3 equations. So they can solve like this beta 2 and also beta 3. And then it runs by like run beta 2, and then they can solve like beta 1 and the beta 3. And then they can run like this beta 3, then they can put the beta 3 equal to 0, they solve beta 1 and beta 2. Okay, so if we're just looking at this voting matrix, we can very easily see the pattern that for the first two, like they align very well, and that's why like it's also like explain as Linbo explained, this can give us a way to identify like which like treatment has zero effect and which does not. Okay, and this tool actually like it's a very clever use of the sparsity, and also the one like really give me a very good surprise and learn quite a bit is this the sparsity also can help us construct the synthetic instrument. Okay, and this is the part I like the most. So they consider a setting like the x2 does not have a direct effect on y, and in this case, so this x2 actually have some very special use. And as I explained here, as I wrote down here, so x2 is equal to lambda2 plus the epsilon 2. Okay, so epsilon 2 is pretty good. It's very organic. It does not directly affect outcome y, and also is not associated with unmeasured confounder u. So that's like a very nice property of epsilon 2. And also for here, like for the factor model, x1 also have such a decomposition, and epsilon 1 is even better because it's only affect y through the treatment x1, and it's not associated with unmeasured confounder. It's by design, it's an instrument variable. But unfortunately, without epsilon 2, we cannot even identify epsilon 1 because epsilon 1 is just the noise or the error of the factor model. So what they use very cleverly is they do a little bit of cancellation of this two u by after they estimating lambda 1 and lambda 2, and then they can cancel this u, and then they can construct this a linear combination of epsilon 1 and epsilon 2. So that's naturally an instrument, but this one cannot really be observed from data. But the left-hand side, it can actually be observed from data. So that's the synthetic instrument idea, and as I'm repeating myself, I like it very much. Okay, and they can just combine this voting and a synthetic instrument. At least that's will help us like enable the identification. But actually, as Linbo explained, it's a lot of computation, and also there could be a bit issue of this post-selection or testing. So this is a clever way. So they find that they can just construct some synthetic instruments instead of doing this, going through this enumeration, which beta is zero, which beta is not zero, and they can construct this, and then they use this constraint optimization to solve this, like give a estimation of the beta hat. Okay, and here I just want to recall that for the construction of synthetic instrument, it needs a very good estimator of lambda hat. So that's the parameter for the factor model. Okay, so this is a bit my takeaway, and it's not the whole logical story, but it's some very nice point I have learned from this paper. And in the following, I would like to provide a bit discussion and connection to something Linbo also mentioned, and also I have been working on for a while. So the first one is related to dense confounding. So in dense confounding, it's very similar to what Linbo is considering here. So the X actually has some effect on Y, and the effect could be sparse. So that means the beta is sparse. And then U is unmeasured confounder. It can directly affect Y. And also there's a key assumption is this unmeasured confounder U is densely affected with Xi. Okay. For example, this U could be like the location or the origin of this population, and in a lot of cases, that's a dense confounding on the Xi is a gene expression level. So there's many background about that. So this is the dense confounding model, and I think the actual assumption we make here is we're assuming that Xi and the Ui, so their association is connected by a dense vector or dense matrix. So that's a key assumption. And then, as Linbo also pointed, like Peter Domagov and Nicola, they have this very cute idea of the spatial deconfounding. So what they do is they do a singular value decomposition on X, and then they remove the top singular values. And that's actually effectively removing the hidden confounding. And if this is a bit too much, so you can just think about they essentially provide a proxy or provide an estimate of U, and then they adjust this, they estimate the U from the factor model, leveraging this dense confounding assumption, and then they put the U to the outcome model, and basically that's the way of adjusting this unmeasured confounder. Okay, but this trimming idea is actually much better in the sense it's very robust. So even though we cannot estimate the factor model well, we cannot estimate how many factors are here, and also how good, like we cannot estimate the lambda and U well. So they still have quite a bit of room to make it work well. I mean, rigorously in theory. Okay, and my first question to Linbo is, I think someone also asked in the Q&A or in the chat. So can we simply estimate U, because now you are assuming you estimate lambda. So can we simply estimate U and then use something, putting this U here, and then include that estimator U in the outcome regression, okay? And the second one is, as a main advantage of the spatial deconfounding, I know it makes different assumption. So I think things gets a bit robust in the sense, even though how many factors we have and how many, what's the factor model, what's the real unmeasured confounder, even though we don't estimate that well, especially this number of factors. So the spatial deconfounding is still quite flexible. It doesn't really require those estimation. Okay, so that's my question is the robustness of the current proposal. Okay, and I just have one more question. And this is also Linbo talk a bit, but didn't provide the formula, I think. So this is the robust instrument. It means like we have multiple instruments. So it's very common in median randomization. And in this case, we can allow that some instruments are invalid. It means they affect a measure confounder, or they directly affect the outcome model. Okay, so in this case, like one way to do the identification is like this voting mechanism or majority rule. We assume that the large proportion of the instruments are valid, but we don't know which are. So that's very related to what Linbo is talking about today. And then we leverage this voting mechanism. For example, here we got 6 instruments, and then we let them vote for each other by solving the similar system equation. And then we can see that the SNP1 and SNP2 and SNP3, they always vote for each other. So we'll choose them because that's the largest group we can find that's agree with each other. And then we can do this like voting and doing the selection. So it's proposing this paper I'm listing here. But the part bothers us quite a bit is how do we construct confidence interval? Okay, so it may be a different problem that Linbo is talking about because he's emphasized again the estimation. But what I want to say is like in causal, we always want to at least do a bit confidence interval. And the question is, how do we construct confidence interval? And the challenge is, if you're just implementing this naive or this very intuitive like selection procedure as I described in the previous figure, so you can easily see the coverage drops quite a bit if the instruments are very hard to separate. I mean, the good instruments and bad instruments are very hard to separate. And then I made a bit progress by doing some like a uniformly valid confidence interval, not relying on the correctness of splicing the instrument. And actually my question is like, maybe more generally like about the uncertainty quantification of the estimator that Linbo and the collaborators have proposed. And finally, I would like to thank the opportunity for me to give a discussion. And I would like to congratulate Linbo and the collaborator again for their very nice paper. Yeah, thank you.
Thank you, Zijian, for the very nice discussion. Linbo, do you want to respond and continue the discussion?
Yeah, sure. So yeah, first I'd like to thank Zijian for a lot of insightful comments. So I think there are several main points. So I first want to comment on the dense confounding model. Yeah. So yeah, indeed, we have some assumptions on the lambda, on the true value of lambda. In particular, we assume that I think any Q by Q submatrix of the lambda or a scaled version of the lambda is invertible. So I think this will correspond to your dense confounding assumption. So let's say I think later we found out that our synthetic instrument may still work under some cases, even if this assumption fails. For example, so if we have some treatments that are not confounded, but we don't know. Okay, so we just include it in the model. Then you can still run this synthetic instrument procedure. In this case, the confounding will not be dense because some rows, I think some columns of that lambda matrix will be all 0. But if you run this synthetic instrument, you will find out that those treatments that are not confounded will appear in the synthetic instrument. So they will become part of the synthetic instruments. So when you run your 2 square, right, in the first stage, you regress your x on this synthetic instrument. So your x hat will also be those original x, unconfounded x. So in your second stage, you will regress your y on those unconfounded x and still get your causal effect estimate. right? So I think we mentioned this in the paper. So if you're interested, but yeah, the short answer is yes. In general, we do need this dense confounding structure, but in some special cases, we might be able to get away with it. So now coming to your questions, the first one is yeah, it's a great question. So so can we? I think this is a first natural question. Can we first just get a U hat and then just regress Y on X and U hat, right? I think this and this is an approach I think taken by a lot of people in some various ways. I think the main approach, I think, just from a causal inference perspective, there's a fundamental difference between the approach we are taking and the approach that this U hat approach. Is that we essentially use the instrumental variable approach, right? So in other words, we don't care about how Y depend on U. We don't care about how Y depend on X. As long whenever instruments can work, our methods can work. Now coming back to this U hat method. So we did a little bit investigation under this U hat method. It turns out that this U hat method will only work if Y depends the model, the dependence between Y and X is linear. So basically so consider a model, let's say Y equals X beta plus U qubit times gamma. So I think due to some special structure of linear models, you can show that if you just regress Y on X and U hat, then you will still be able to get a consistent estimate. But not if you regress Y on X and U hat cubic. Okay, so it's interesting that no matter doesn't matter how Y depends on U. Let's say Y depends on U through a cubic or Q square term, right? You still need to plug in the U hat, and you will still be able to get a consistent estimate of beta. But this is only true if Y depends linearly on X. So if Y, the dependence between Y and X is nonlinear, right? Let's say this becomes, it's exponential or some other forms. Then you can still use an IV, use a non-parametric IV to get rid of U, right? This the logic will still work because IV will work for linear causal effects, but this U hat method will no longer work. So in the paper, we actually have some simulations showing comparing our method SIV and this U hat method, and you will see that this U hat method will fail to work when the dependence between Y and X is nonlinear. And coming to the second question of this robustness to U and Q, of course we don't estimate U, so there's no estimation of U here. So we do need to estimate Q. But I think our method in any practical cases will be very robust to Q in the sense that you can always take a conservative estimate of Q. Because the identification assumption says your S needs to less than P minus Q, right? So if you are not sure about the estimate of a Q, you can play it safe and get to get the most conservative estimate of Q multiplied by 100. Okay, and the UJ will still work, right? If in the data example I show you, right, S is 5, P is 3000. Our estimation of Q is 3, right? If you are not comfortable with 3, you can call it 300. You will still figure out 5 is less than 3000 minus 300. So we have a lot of rooms to make mistakes about Q. This is because usually the distance between S and P minus Q is very large. And now let me quickly comment on your last question about the inference procedure here. Yeah, I think this is very interesting work. And I think actually we thought about how to construct confidence interval, but after hearing about your comments, I think this can be a promising direction because essentially, so to talk about post-action inference, right? You worry about the local alternatives, right? So let's say if some betas non-zero, but they're very close to zero at a certain rate. Right, so let me call this a locally invalid native control treatments. Right, so by the way we construct the syntactic instrument, this will translate to the instruments, some of the instruments corresponding to that treatment being locally invalid, because any effect from this treatment to outcome will translate into direct effect from the instrument to the outcome. Right? If you think about let's say, if we think about our case, let's say if x2 has no effect on y, right? This beta 2 is 0, then x1 minus whatever alpha 1 divided by alpha 2 x2 will be a valid instrument. Now, if x2 has a non-zero effect on y, then the same thing will be invalid instrument. And the degree of invalidness will be exactly correspond to the effect size of x2 on y, because that's the direct effect from the instrument to y.
I see.
So I think in some degree, I think there is a correspondence between our setting and the setting you consider here, right? Because I think you are considering locally invalid instruments.
Yeah.
And I think here, if we think about, we need to consider locally invalid native control treatments. And I think there is a correspondence. So I'm happy to think about this further, and maybe we can talk more. Yeah.
Thank you so much, Linbo, for the insightful comments.
Yeah, thanks a lot. Yeah.
Then I will stop share.
So good. Yeah, thank you so much again, Linbo, for the very nice talk, and Zidong for the insightful discussion, and also Dinke for handling the many interesting questions. So I think it's a good time to wrap up today's seminar. Let me, before we wrap up, let me share the screen again and introduce our next seminar. So next week, we are pleased to have Professor Zijun Gao from USC Marshall to talk about explainability and analysis of variance. And as our discussant, we will have Professor Art Owen from Stanford. We look forward to seeing you again next week. Thank you so much.
Thank you.